All right, greetings everyone. I am Ryan Su and I'm your host for this webinar. Welcome and thank you for attending this session titled Thermomechanical Development of Bio-Based Polymer Materials, Focus on Algae Biomass. I would like to remind everyone that this webinar is being recorded and will be made available as soon as possible. Just a brief introduction to MDPI. So MDPI, whom is a pioneer in scholarly open access publishing and has supported academic communities since 1996. We are based in Basel, Switzerland, and has the mission to foster open scientific exchange in all forms and also across all disciplines. As for the journal, Polymers is a peer-reviewed open access journal of polymer science published semi-monthly online by MDPI. We have an impact factor of 5.0, and we'll have an updated score early next month as well. We have a site score of 6.6 and a Swifty 12.4 days for time to first decision and 3.6 days for acceptance to publication. As for today's schedule and outline, we will first have our chair introduce the webinar, follow up with our keynote speakers presentations, and a Q&A session at the end where the chairs will lead the questions. Just a quick reminder that you can please indicate which speaker the question is directed to and leave your questions in the Q&A tab beside the chat. We will address all these questions at the very end in the question and answer section. So feel free to add any of your questions or inquiries during the talks, and then we will address them one by one afterwards. This webinar is based on a special issue by Polymers, and if you're interested in this special issue or any related special issues, please refer to the webinar website and to contact us for more information. We are grateful to have both Professor Carlos Bengoechea and also Dr. Estefania Alvarez Castillo to chair this webinar today. Professor Bengoechea is a lecturer and researcher at the University of Seville, Spain. He belongs to the Rio Tech Group, TEP 229, which has a broad expertise in rheological characterization of multi-component products. In the last few years, he focused on developing and characterizing green plastic materials from bio-wastes. We also have the honor of Dr. Alvarez Castillo from the University of Seville, who has a 5-year degree in chemical engineering and also a master's degree in food industry and technologies from the same university. Her research focused on the thermomechanical and rheological characterization of superabsorbent materials based on bio-waste and food industry, from the food industry. We are fortunate also to have our 3 speakers today, and the first one is Mr. Ismael Santana from the University of Seville. We have Miss Julie Krefelek from the University of Vigo, and also Miss Christiana Nuns from the University of Lisbon. Thank you, Professor Bengoechea and Dr. Alvarez Castillo for agreeing to chair this webinar. Without further ado, I give the floor to Professor Bengoechea and Dr. Alvarez Castillo.
Welcome to this webinar. With this frame, we did the Polymers special issue entitled Thermomechanical Development of Bio-Based Polymer Materials. This webinar focuses on the green plastic materials based on algae biomass. Interest on algae has increased due to the different factors such as their sustainability, versatility, or efficiency. This is Estefania Alvarez from Reotech Research Group from the University of Seville. I'm one of the special issue next to my colleague, Carlos Bengoechea. Now I'm going to introduce the 3 speakers that we are going to have the pleasure of listening. They are from 3 different research groups. First, Ismael Santana, who is part of Reotech Group at the University of Seville in Spain. Then Julie Krefelek from the Chemical Engineering Department at the University of Vigo, also in Spain. And to end with Professor Christiana Nunes from Food and Feed Group from the School of Agriculture in Portugal. At the end of the 3 talks, there is time for a question and answer question. So if you want to participate and make any question, please write it down in the chat, indicating for who the question is. and the speaker will answer it later. So now let's start with our first speaker. He is from the University of Seville. He is my colleague Ismael Santana, who is finishing his PhD focus on the Rugulopteryx okamurae, an invasive species in the south of Spain. And today he's going to tell us about the alginate extraction and the characterization of calcium alginate gels from the invasive seaweed Rugulopteryx okamurae. Hello, Ismael. Can you share your screen?
Sure. Well, as Estefania has presented me very well, I'm Ismael Santana, part of the Riotech group from the Chemical Engineering Department of University of Seville. And together, along with Manuel Felix and Carlos Bengoechea here present, we've worked in the alginate extraction and the characterization of calcium alginate gels from the invasive seaweed Rugulopteryx okamurae. For the beginning, I'm going to make a small introduction. Well, actually, the issue of the marine and seaweed blooms are a growing biological phenomenon in many regions of the world, especially in Spain. For example, of the 400 or more or less invasive species of seaweed existing right now, 50 of them can be found around the Iberian Peninsula. This issue of the invasive species of seaweed in short term can mean a very explosive and occupy on the seabed surface, especially in our case in the Strait of Gibraltar, and doesn't also produce this kind of, well, it's just not a problem of environmental because of the affection of the marine biodiversity, but also the waste accumulation in the coast. In long term, on the other side, some species, some native species can be recovered, integrating the invasive one, but the changes in this case are being very, very abrupt. For example, in 2015 was the onset of the proliferation of the Rugulopteryx okamurae here in the Strait of Gibraltar, which coincides with the year where it was registered the highest temperature peak of the last 20 years. Also, for example, to take a look of the problematic that it's causing in Ceuta, more than 5,000 of tons of Rugulopteryx okamurae waste were collected from the coast. So it just doesn't affect the marine biodiversity. For example, also these temperature changes due in fact to the global change of the greenhouse effect affect also to the coral reefs or estuaries that can create voids when those invasive seaweed can take advantage of it and displace the other native species, affecting also to the fishing industry and to the tourism. So what can we do to take advantage of this situation? Well, this seaweed can be collected and try to turn them into a source or raw material for different applications, as can be some bioplastic that we already made a couple of years ago. And for example, in this case, as Rugulopteryx is brown seaweed, it means that almost 40% of this dry weight is alginate. So we decided to extract it and turn it into some gels with many different applications on the industry. We want to thank Ismael Achero from the Cente IFAP El Toruño in the Puerto de Santa María, Cádiz, for providing us the seaweed, which are collected in the Punta del Carnero, also in Cádiz. And with that, I'm going to make a brief index about what are we going to do. First, I'm going to talk about the extraction of the alginate from the Rugulopteryx okamurae. Then I'm going to talk about the characterization of this alginate by different methods. We use infrared, thermogravimetrical analysis, nuclear magnetic resonance, and determine the molecular weight by calculating before the intrinsic viscosity. Once characterized, I'm going to talk about the gelation, especially about the rheology of the solution to gel transition. And over the gels, we're going to talk about its rheological properties and the water uptake capacity and the water holding capacity after freeze drying those gels. The extraction begins with the freeze-dried and milled seaweed, which is treated soaking it into a 2% weight formaldehyde solution during 24 hours in order to remove the pigment. After that, we try to alginate the proteinate the alginate with a solution of 0.2 molar of hydrochloric acid during 24 hours. Between each step, we made a centrifugation of the solid and wash it with water very cool. After the protonation, we centrifugate it again and wash it again to start the extraction by adding 2% in weight of carbonate sodium during 5 hours at 65 degrees stirring. After letting temperate for until room temperature, we precipitate the alginate by adding 3 volumes of ethanol. Finally, this precipitated alginate is soaked it's drying in an oven for 50 degrees during overnight, and we freeze dried it in order to obtain as a dry powder. All this extraction gives us a yield of 16 or 19% of the seaweed obtained, depending on the season when the seaweed is collected. So about the characterization, the first one I want to talk about is the infrared. This is the typical infrared profile we see of alginate, with a special interest in the OH stretching vibration of the bonding OH at 3,400 centimeter minus 1. Also, an special one are the asymmetric and symmetric stretching of the carboxylate bonding at 1,400 and 1,600. This is the typical profile of an alginate to determine that we actually have an alginate extracted. And just to comment something, in the case of the extracted one, we have some residue for sodium carbonate from the extraction, as the peak at 1,600 and the 879 is slightly thermogravimetrical analysis. Well, we found here, I can show the peak. 3 important peaks are shown here. The first one is at 80 degrees and corresponds to the dehydration of the alginate, which means lose about 10% of the weight, more or less, of the dry weight. At 249 degrees, we have an endothermic peak, a biggest one, which implies that the composition of the alginate, leaving us with a loss of around 20-30% of the dry weight of our alginate. And finally, over the 300 degrees, we found 2 peaks around 346 and 465, corresponding to the formation of carbonate residues, losing about another 10 or 15% of the weight. Finally, we make a nuclear magnetic resonance, which is an important part because it leads us to determine the purity of our alginate, comparing it with a commercial one. Also, to understand this plot, it's important to understand the structure of an alginate. It is composed mainly by 2 different groups, the glucuronic acid and the mannuronic acid, which are groups in which we call the G groups and the M groups. The influence of those groups has been reported several times. For example, Lee reported those alginates with a higher number of G blocks produced more stable alginate yields because the fibers are stronger due to the kind of bond existing between the G blocks. I mean, the bond form is an axial bond where here can be seen, who leads to a buccal type ribbon structure with some voids where calcium divalent, or any divalent calcium actually, can fit into it and form this structure we call what it's called by Rees since 1982 as an egg box, which gives a very stable and structure compared to those with more M groups. That's why it is very important to remark the fraction of G groups That's what FG. RO, it means regulatory hexagon, right? And the MG, that it's just the relation between the M groups and the G groups. In the plot here, we can see the typical peaks of the RGNA profile to compare this and to make sure that we are analyzing actually RGNA. We observe G1, GM5, M1, and G5 that are all only different groups of G blocks or GM bonds groups into the structure that are common in almost every RGNA structure. And we, using the area under the curve, we determine the purity of our RGNA, which leads us to a 74% purity compared to the commercial one. And finally, we wanted to determine the molecular weight, and for that, we first calculated the intrinsic viscosity using the Fedor's equation, as you can see here, where eta Rf is the viscosity of a capillary viscosimeter and eta is the viscosity of arginate. Using a capillary viscosimeter, we made some solutions of different concentrations of arginate with water and build this line you can see here. And by using the slope of this line, we obtain the value of the intrinsic viscosity using the Fedor's equation, which gave us a value of 2.03 deciliters per gram. Once we have the intrinsic viscosity value, we can calculate the molecular weight with the Mark-Howing-Saccharades equation, which relate the viscosity with the molecular weight, where you can see here, where K and constants depending on the type of alginate. There are several studies trying to find a common value for those constants, are also the intrinsic viscosity that we already calculated, and leading us to a molecular weight of 94,874 grams per mole, which is an actual value for an RGNA molecular mass, and it can reach even until 100,000 grams per mole, which is a bit more. Here, to compare the commercial RGNA, were also calculated, and we obtained more or less similar values, a little lower. And after that, once we have characterized our RGNA, we decided to proceed to make the gels. For it, we prepared a solution of calcium chloride and introduced it inside a gel, a dialysis bag, with the sodium arginate and water solution. We prepared 3 different concentrations, 0.5, 1, and 2% in weight. Letting the calcium diffuses into the dialysis bag through the pores, and it's led the reaction. It's soaked for 24 hours. You can see here an example of 1% arginate gels, how it looks like. When we let it soak for just 1.5 hours, we didn't obtain a full structure. As you can see, it didn't diffuse into the dialysis bag, but we made different tries at different times until we obtain a solid and homogeneous block of arginate gel after 24 hours. That is what we used for the study. This gelation is also were studied by using the Discovery H3 rheometer of the instruments, making a phase change study at 20 degrees, 50 revolutions per minute during 500 seconds, with a rotating vane geometry. Obtaining this plot, as you can see here, the higher percentage of the arginate and the higher viscosity lead us to a higher value of torque. Also, in the first stages of the test, you can see an abrupt increase in the torque because of the contact between the calcium and the arginate at the first stage. These start making contact with the walls and the plates of the blades of the vane until we obtain an homogeneous gel. It is stabilized at the very finish, at the end of the plot. Sorry. You can see here how it finished at the end, and we obtain a homogeneous gel stick to the blades of the of the vein geometry. Also, it's important to remark here too how the sorry, the viscosity, well, the viscosity of our seaweed as it was calculated before during the intrinsic viscosity is above the commercial medium viscosity one. So now going forward to the rheological properties of the gels already formed, we used a Hackmars 40 rheometer from Thermo Fisher Scientific. We made some frequency sweep test from 0.1 to 10 Hz at 20 degrees using parallel rock plate of 20 millimeters of diameter. And we made those assays just after obtaining the gels. After the 24 hours into the calcium chloride solutions, we measure them. We obtain this plot where we represent the storage and loss modulus with the frequency. And it's always present a predominant elastic behavior. The storage modulus is always above the loss one. The higher modulus is related to the concentration, as the high modulus, the high concentration, where the 2% is always above 1% and always above 0.5% in all the cases. And also the regulatory secondary alginate, it's above the commercial alginate one, as happened before in the Turkey plot, with the value of the intrinsic viscosity determination. So with those gels, after we made all the rheology properties, we decided to make a water uptake capacity and water holding capacity study. For it, we freeze dried the gels. After that, we soaked it 24 hours in water. For the water holding capacity, we centrifugated at 1,000 revolutions per minute. We found out this results you can see here. I'm sorry, I'm going to remove the one. We in the first plot, we can see in red the water uptake capacity, and in the gray the soluble material loss is how many mass we lost during the immersion in 24 hours in water. And we determined how, when increasing the weight percentage and the viscosity of the samples, there is a decrease in the values of the water uptake, the soluble material loss, and water holding capacity. This last value, the water holding capacity, it has an exception in the case of our regular series with the viscosity. As you can see, it's the blue one. It looks more like the middle point between the low commercial and the low viscosity commercial and the medium viscosity commercial alginate. But in the rest of the case, you can see how always the higher viscosity and weight percentage, there's lower the values of the water uptake, soluble material loss, and water holding capacity. In the case of water uptake, it's very interesting because we are always in the lower values of weight percentage, above 1,000%, which is a very good value for water uptaking capacity. Even also at 1% of the regulatory extracted one, we reach the 1,000, which is also a very good value. So to finish, just I'm going to conclude to read the conclusion that the extracted alginate is obtained with a purity of 74% with a slightly different structure, where we have a higher fraction of glucuronic acid, the G block, with a molecular weight of 94,874 grams per mole. These extracted alginate gels have a higher viscoactive moduli values than the medium and the low viscosity commercial gels, which this and the previous conclusion are both related with the structure and the amount of glucuronic acid blocks in the structure of our alginate compared to the commercial ones. And the water uptake capacity and the holding capacity are higher in low viscosity alginate gels. And as a summary, to know that it is possible to extract alginate from the invasive seaweed, Rugulopteryx okamurae, and obtain gels with suitable mechanical properties and water uptake capacity and holding capacity, even comparable with those commercial alginate. So thank you very much for your attention. I'll be answering your question at the end of the presentation. Thank you very much.
Thank you, Ismael. Thanks for the presentation you make of your results. and hope the audience will have questions for you at the end of this webinar. And now it's time to welcome our next speaker. She is Julie Kefalek from the Chemical Engineering Department of Universidad de Vigo. And her work has been focused on the development of biocompounds and biopolymers based on algae. And her speech today is entitled Microwave Assisted Extraction of Biopolymers from Brown and Red Algae. Hello, Julie.
Hi everybody. Let me share my screen. So yeah, I'm currently working on the ECUDOS group of the Department of Chemical Engineering of the University of Vigo. And thank you for inviting me. I'm glad to present a small part of our works today. So I will explain a bit how we can extract biopolymer from algae with microwave assisted extraction. So just a small reminder, the biopolymer we can obtain in algae depends on the type of algae we are working on. In green algae, we can find, for example, ulban. In red seaweeds, we can find agar and carrageenan, and brown series are mainly made of laminarian, fucoidan, and alginate. And today I will focus on the extraction of carrageenan and alginate. So what were our raw materials? So we first work on Euschema spinosum industrial waste. So it were wastes from the extraction of carrageenan, because Euschema spinosum is a red seaweed, so we can extract alginate from her, and we can find this seaweed in the Indo-Pacific region. And its algae is already mainly processed for the extraction of carrageenan. So the carrageenan, we can find it in the cell wall of red algae. It's a unique biopolymer made of disaccharide units of sulfated galactane. And there are different types of carrageenan, depending on the number and the location of their sulfate groups. And why carrageenan is interesting? Because it has some bioactive properties, like antioxidant and antitumoral properties, but it's also widely used in the food industry as a stabilizer and texture forming agent. And we also worked on Daria pinnatifida, which is a brown seaweed. We can find it everywhere around the world because it's an invasive species, and even if its native area was the Indo-Pacific region, now we can find it all around the world, and it's also known as wakame. So yes, it's an edible brown seaweed, but it's also a process for the extraction of bioactive compounds and alginates. So alginate is also a polysaccharide that make the cell wall of brown algae, and it has been already said, it's a unique polymer made of manuronic and hyaluronic acid block. And yes, the motif of alginate chain can change a lot. We can find different occurrence of manuronic blocks, hyaluronic blocks, and a mix of hyaluronic and manuronic acid blocks. And alginate, he has also quite interesting properties, gelling properties. It's biocompatible and biodegradable, so it's useful in biomedicine or in the food industry too, for example. And to extract both carrageenan and alginate, we use microwave assisted extraction because it makes it possible to perform a really quick extraction here 5 minutes extraction compared to a conventional extraction. It's a pressurized microwave, so we were able to achieve temperature, quite high temperature. Between we extracted the biopolymers between 120 degrees and 220, and we use only water as solvent for environmental issues. So here, what was the process to perform the industrial rest of Euschema spinosum. So we performed first the microwave extraction, and then we, from the liquid fraction, we precipitate the carrageenan with ethanol, and we obtain a carrageenan, and then we made some gel from this carrageenan. So we can see that the extraction temperature has a great influence on the yield of the extraction yield of carrageenan, because we obtain at maximum 118% of carrageenan at 160 degrees, when we obtain only 1% at 200 degrees. With infrared and NMR analysis, we were able to characterize a bit more what we precipitate. And the carrageenan was mainly made of iota carrageenan, 75%, mu and nu carrageenan precursor, and kappa carrageenan. And this information, it's quite logical, because Euschema spinosum is the main source of iota carrageenan, and it's quite important knowing which kind of carrageenan we have before making gel, because it influences a lot the gelling properties of the carrageenan. So with polymer, we to characterize polymer and gel matrix, we perform some rheological measurements. So first, basic one, steady state viscosity. So here the upper plate of the rheometer was rotate in one way, and we measured here the torque needed to maintain a known speed and increasing the speed, and so we were able to determine with this data the Keir stress, the Keir rate, and then the Keir viscosity, and we can see, for example, if more torque is required at a higher rotation speed. In that case, we are working with a dilatant material. And on contrary, if a smaller torque is required at higher speed, we are working with pseudoplastic fluid. And to characterize more, in that case, the gel matrices, we perform the oscillatory Keir measurements to know the viscoelastic properties of the samples. So here it was an oscillatory measurement, so the upper plate of the rheometer was rotating in both ways, which can be represented as a wave, as a sinusoid. And here we apply the control stress, and we measure the angular displacement to deduce then the Keir strain. And what we observe in that case is the difference between the phase shift between the maximum Keir stress and the maximum Keir strain, and that indicates us if the material is the component of the material in terms of elasticity and viscosity. For example, if we have an elastic hair band. When we applied a Kier stress, the maximum strength we applied, and we have the maximum the deformation at this strength. There is no phase shift between the maximum strength we applied and the maximum deformation response of the material. So it's a property of elastic materials, and when there is a phase shift between these two maximum, it means that we also have a viscous component. And this modulus, the elastic modulus G prime and the viscous modulus G second are interesting to characterize gel matrix. So we will see later how we can apply that. So carrageenan, how can it gel? So first, random calls have to form helices with hydrogen creating hydrogen bindings, and then when it's a unique polymer, so we have to help it forming gel, we have to add some salts. So adding a potassium cation in our case, we make possible the helices to bind with each other, creating a three-dimensional network. And the properties of gel are really different in function of the different units of carrageenan we have, because for example, the iota carrageenan has two sulfate groups, when the iota ones, the kappa ones only has ones. So it creates different type of bindings, and also different more flexibility in terms of in the case of the kappa one, because there is only one sulfate group, so only one binding point between the different helices aggregated. So it makes it possible for these helices to orientate themselves and create other bindings, while when with the kappa one, with the iota one, for example, where there are two sulfate groups, so the bindings are a bit more rigid. So maybe this chain were not able to orient themselves to create a greater network. So that's why, for example, iota gel are usually weaker than kappa gels. And so here you can see the influence of the extraction temperature on the viscosity and on the gelling properties of the carrageenan. So we can see that the viscosity was much higher for carrageenan extracted at 140 and 160 degrees. And it can be explained by what I said just before, how these disaccharide units of carrageenan are organized in the chain. And here on making gel with 1% carrageenan and with potassium cation at 0.1 molar. We can see that the strongest gel here is the one obtained at 142, and followed by the one at 160 and 120. So now the alginate parts. So we also made some gel matrices with alginate extracted by microwave 2 from Undaria pinnatifida. So we precipitate the alginate from the liquid phase obtained after the microwave extraction with a calcium chloride. So we were then able to recover it, to dry it, And to make gel, we wanted to make it with sodium alginate because it modifies also the properties of the gel are different in function of the type of alginate. So to obtain sodium alginate, we first dissolved the calcium alginate we had. We had lemon juice to acidify the medium to obtain alginic salt, alginic acid, and then adding sodium carbonate, we were able to recover sodium alginate. And so it has already explained. It has been already explained in the first presentation. So yeah, the gelling properties of the alginate depends on the block of manuronic acid and glucuronic acid of the alginate chain. To gellify, the alginate must have at least around 20% of glucuronic blocks, because as it has been explained, it creates more stronger bondings, creating like cavities for the cation. But the gelling properties also depends on the cation we had to form the gel, because, for example, calcium can bond with glucuronic blocks, but also with dimers of glucuronic and manuronic acid, while, for example, strontium can only bind with glucuronic dimer of glucuronics. So there is a lot to play with to modify the gelling properties of the alginate. And in our case, we use calcium to gellify the alginate. And to know, to tend to predict a bit the properties of the gel we will make. With an NMR analysis, we were able to quantify the glucuronic and the manuronic blocks of our extracted alginate. And we can see that the extraction temperature has an influence on the proportion of glucuronic and manuronic acid blocks, and that the alginate that had a greater number of glucuronic block was the one extracted at 160 degrees, and it was also the closest to the commercial one. So we can suppose that we will obtain a stronger gel using the alginate obtained at 160 degrees. And yes, we can compare that on the frequency sweep of the gel matrix made of 1% sodium alginate and adding with in a dissolution of calcium. So we can see that the elastic modulus, the greatest elastic modulus, was obtained for the commercial alginate, and followed by the alginate obtained at 160 degrees. So the two with the greatest number of glucuronic block. And we can also see that there is almost a 10 factor between the elastic modulus and the viscous modulus, and that these two modulus are invariant with the frequency. So we can say that we obtain gel like with intermediate strength gel. And then we decided to incorporate the residual solid we obtain after the extraction of the alginate. So we separate the liquid phase and the solid fraction. So we decided to incorporate some of these solids into the gel matrices to see the modification of the rheological properties. And we can see that, so we did that only creating the gel with the alginate obtained at 160 degrees, which has the best rheological properties. And we can see that the temperature at which the solid was extracted has an influence on the strength gel because here when we incorporated the solid extracted at 120 to 160 degrees, the gel has a greater elastic modulus than with the solid extracted at a higher temperature. And it can be explained by the composition of the residual solids, because they are we can see that there is a higher mineral content in these solids extracted at 120 to 160, so it can help the alginate to form a stronger gel, and which can explain the rheological properties of the gel. So to conclude, we can say that microwave-assisted extraction is a quite suitable technique to extract both kerosene and alginate. And these two polymers were able to form gel matrices using a cation to gelify. And this kind of matrices can have interest in cosmetical, food, or biomedical industries. So thank you very much for your attention, and feel free to ask a question later.
Okay, thank you, Julie, for your nice and interesting presentation. And now is the turn of our last speaker, Professor Cristiana Nunes. She's coming from Food and Feed Group at the Higher Institute of Agronomy in Lisbon, and she has a wide experience in the use of algae as a poorly exploited source for the development of high added value products. And today she is going to talk about adding microalgae biomass into cheese impact on the thermomechanical behavior.
Okay, good afternoon. I'm Cristiana Nunes from the University of Lisbon. Are you listening? Yes? Yes, okay. From the University of Lisbon, and I'm going to talk about the impact of adding microalgae biomass on the thermomechanical behavior of cheese. And first of all, I would like to thank Carlos and Stefania for the invitation. Well, microalgae, as all of you know, are incredible food sources also. They are sustainable, they have a lot of nutritional benefits, and they can be used for food innovation. And now they are considered as emerging innovative sector of the blue bioeconomy. So they are used in many food applications. But in fact, besides their nutritional benefits, they can impact the rheological and texture behavior of food, and also the sensorial profile. And in fact, in my opinion, this is the main issue related with microalgae incorporation in food, is these sensorial changes, because in fact, a recent analysis of opinion in social media regarding the consumption of microalgae-based food products indicated that are very few negative feelings, most of them related to smell. And we have the problems due to aroma, taste, and also coloration. And maybe it's because of that there are only a few examples of microalgae containing foods produced at industrial scale. And even in the scientific publications, the solution is usually overcome the sensory issues using algae at low concentrations. And the typical, we have many different microalgae produced using different technologies. And of course, there are a lot of different and typical odors, flavors of microalgae, but many of them can compromise their incorporation on food. And we have a lot of them, like you can see here in this figure. Marine, herbaceous, floral, fermented, and the fishy flavor is often the worst problem. As I was saying, in fact, the technological processment of microalgae can influence a lot on their sensory profile, and today we have some solution to overcome this problem. Usually microalgae are produced by autotrophic growth, but it is possible also to use fermenters to use the autotrophic conditions, introducing a carbon source. And also with controlled DNA manipulation, we can in fact obtain microalgae, not all microalgae, but some, like for example chlorella, that can have. There are smooth. Some companies call them smooth chlorella. Because they have smooth colors and tastes. Of course, also it is impossible to it is important to highlight that also the processing conditions, like the centrifugation, the filtration, and also the drying conditions, if it is used spray drying or solar drying, freeze drying, of course, it will influence a lot on the mechanical also, but also the sensory properties, and of course the cell disruption. It is a very important downstream process because microalgae usually have cell wall, and it is important to have an increased bioactivity. It is important to disrupt this cell wall, and several methodologies can be used, like bead milling, ultrasound, high pressure homogenization, enzymatic methods, and so on. So our in this project that I'm presenting now, our objective is to apply a new methodology to obtain healthy, sustainable, but also tasty microalgae food. Because in fact, as I said before, we have nutritional benefits. We have to study, of course, it is the frame of this webinar, the impact in terms of mechanical behavior, texture, but also if we forget the sensorial changes, nobody will eat microalgae food enriched with microalgae. So we need strategies to engage the consumers to overcome these issues. Usually, as I said, the current solutions are the low inclusion rates, the encapsulation of microalgae biomass, but in our group, we have experienced we have students from the gastronomic science, and they developed several meals, several disrupted experience. This is only one of them, developed by our PhD student. She is also a chef, Sonia Oliveira. And this was an amazing, these are amazing products with microalgae. And this is important, of course, but our actual objective is to use microbiology for industrial applications, not only for this experience in terms of gastronomic science, but also to launch into the market new food products with microbiology incorporation in interesting levels, using interesting levels. This is our main goal. So, as I said before, there are other chemical and biochemical processes for the deodorization and decolorization of microalgae. For instance, as you can see in this image, we have the autotrophic chlorella in this dark green, and this is in the middle. We have the smooth chlorella. This is from All Microalgae Company in Portugal. And this one is produced with heterotrophic conditions, and also they offer a yellow one, and also it is not here, but also a white one for different applications. But of course, not all microalgae can be processed using these technologies. In our group, we also studied the possibility of using ethanolic extraction to overcome this problem. It was include this microalgae biomass produced by ethanolic extraction was included in bread applications. Presently, we are also working with ultrasound extraction to overcome the sensory issues, and we are including the both fractions in emulsions, in bread, and also in pasta products. And at the present moment, we have a project, the YAM algae project, where we are trying to use the enzymatic treatment to overcome the sensory issues. So the objective of this YAM algae project is to improve the sensory quality using enzymes. And in fact, we want to reach higher sensory analysis scores in terms of global appreciation and buying intention. This is our main goal, and we selected two different study cases: bread and also cheese. And today I will talk about the cheese products. So we are not alone. This is a partnership between Norse in Norway and Pagaretti Microalgae Solution, a small microalgae company in Portugal. And in terms of research institutions, Instituto Superior de Agronomia, University of Lisbon, where I am from, and also Instituto Superior Técnico, also in Lisbon. And these are the tasks of this project. And of course, we want to perform the proof of application, and we want to test the sensory quality of the food products, bread and cheese, after and after incorporating this biomass, before the enzymatic treatment, after the enzymatic treatment, with we are expecting higher sensory scores. So in bread, just to present the project, in bread we are working with wheat bread, and also wheat bread but incorporating sourdough. And we want to study the impact of microalgae on fermentation. on the bacteria, and of course the impact of microalgae in terms of dough and bread structure, in terms of nutritive value and bioactivities, and also in terms of volatile compounds and sensory profile. Well, in cheese, we had a previous project with an important Portuguese company, a cheese Portuguese company, and we have developed this cheese, Ripnut cheese, and also Fred cheese. It was a big success. They will be launched into the market soon. We are expecting it, and this was done without the enzymatic treatment. But our goal, as I explained before, is to improve, to increase the levels of microalgae, not in the Ripnut cheese, because in this case, because of the fermentation, we are working with only 1% in milk, but in the final product, in cheese, it is around 10 to 15%. It is too much, as you can see here, looking at the color. But in other products, like the fresh cheese, we would like to increase these levels. Also in cheese, to explain, we want to understand better the impact of microalgae in terms of the microorganism responsible for the fermentation, and also, as usual, the impact on cheese structure, on the nutritive value, and also the impact on the sensory profile. Héctor Hernandes is our PhD student who is working with cheese. First of all, he developed this fresh cheese called halloumi. I think you know. It is traditional from Cyprus, and it is usually consumed after an eating process. It is grilled. It is a substitute for meat, usually chicken meat. And as you can see, we incorporated 1, 3, and 5% of Chlorella vulgaris. It is a very known microalgae, and also more recently he incorporated microalgae in camembert like cheese. It is a completely different cheese because it is Ripn, and halloumi, as you can see, as you know, is a fresh cheese. So in milk and dairy products, there are some publications about incorporation of microalgae in yogurt, in cheese, but there are a lot to study because in fact we have this problem, the change in the mechanical behavior and the sensory properties when incorporating this microalgae biomass. And the experience we have with this Portuguese company is that it's very difficult to adjust the food processment because algae in cheese will retain more water, and so it is necessary. It was in this company, they produced this at an industrial level, and it was necessary to adjust the coagulant, the salts added, and so on. It was not easy. It is a challenge, but it is possible, and we had very good results, in fact. So, due to this water retention, we will have changes in mechanical behavior, and of course, when using algae, we have always these sensory issues. The good news are the bioactive properties, of course, because usually we can increase the antioxidant profile, the phenolic profile, the minerals, the protein, it depends on the cheese, but we had, of course, and we are obtaining very good and promising results. I will show you some of these results. This is for halloumi and also camembert cheese. And as you can see, these are results from the TPA, texture profile analysis, using a texturometer. And as you can see here, in halloumi, with 1% level, we had no significant differences, but when incorporating higher levels, 3 and 5%, we had a decrease in terms of cheese hardness. And it is in the same in the camembert-like cheese. The levels are different, but for 5 and 7% in this case, we obtain a lower hardness. And as I explained, this was due to the high water retention due to the higher content in terms of protein. Because when incorporating microalgae, we are adding protein, and so we will have higher water retention. In terms of oscillatory rheology, as you can see here, these results are in good correlation with texture, with hardness, because in black we have the control cheese without microalgae, and in green colors we have, this is for halloumi only, we have the cheese incorporated with microalgae in different levels. And as you can see from the table where we adjusted the power law equation, we can see that we had a decrease in terms of alpha prime when it decreases when the microalgae level increase. So the structure will be a weaker structure when compared to the control. And in terms of B prime values, they rise when incorporated chlorella at 5%. It means that cheeses became less elastic and less stable. Also, we performed temperature sweeps, eating temperatures, because halloumi, as I said before, is usually consumed after thermal processing. Also camembert, in several gastronomic applications, camembert is eaten. So we tested the behavior during the eating process. And as you can see here, we adjusted the Arrhenius equation, and there are no differences between the activation energy and the fat melting point is not so different. There are small differences, and all the cheeses without and with different levels of algae were in the range of 42 and 43 degrees Celsius. So the algae biomass incorporation had low impact on the thermomechanical behavior. These are good news, because we want cheese with microalgae, but with not so different thermomechanical profile. In terms of the nutritional value, this is only for halloumi cheese, but as you can see here, I was explaining this before, we had an increase in microalgae, in protein from microalgae, as you can see, a significant increase. And also in terms of ash, it is related with minerals. So we had, I am not showing this here, but we also have the results for the different minerals. And in fact, we had an increase in terms of mineral profile in these microalgae-rich cheeses. In terms of moisture, fat, and pH, the difference the changes are very small. Well, the good news are the bioactivities. We performed the antioxidant using the FREP assay, the total phenolic compounds, and the pigments, chlorophyll A, B, and carotenoids. And as you can see here, when increasing microalgae, even in these cheeses, alumi cheeses, which were heated, we have an increase in terms of these parameters, these bioactivities, and these, of course, are the best news. The sensory analysis is always very important, and in fact, as you can see here, the control and the cheese only with 1% had the highest global acceptability, but even so, we had high similarity of the taste and aroma between the control and the cheese with 5%, and we consider these very promising results, of course. From this graph of purchase intention, as you can see here, 30 and 53% of the taster would probably buy the cheeses incorporated with 1 and 3% of algae. So, in conclusion, about the impact of adding algae, Chlorella vulgaris in cheese, we saw that it has impact on the mechanical properties. Cheeses with algae had a weak gel-like behavior, and it was affected, this gel-like behavior was affected by the algae. We have a lower structure material. The nutritional composition is also affected by this algae addition, increasing protein and ash contents. And cheeses with low percentage of algae incorporation are more accepted by taster, by consumers. So we have here the importance of this enzymatic treatment that we are presently working on, and in the future we would like to increase this sensory profile. In fact, just to explain a little bit of this, we are also working on the volatile composition, not only from the algae, but also on the final products. Camembert cheese, this is only an example, and also our breads. And in cheese, we have good news because, as I said before, this is not easy to present and to discuss here, is not our objective, but just to tell you that it is more difficult to incorporate microalgae in bread, and the volatiles compound profile depends too much on the species that we are incorporating. This is the bread with no algae. This is Nanochloropsis or Microchloropsis gaditana. This is Chlorella. This is Tetracell michui. And we have, as you can see here from the pics, we have a completely different profile of these breads depending on the algae that we are incorporating. In cheese, on the left side, in the cheeses, comparing with the algae, in the bottom we have the algae, and these are two different cheeses, the control and the one incorporated with 7% of chlorella. And as you can see here, the difference are not so wide, because in fact we have the fermentation contributing to the balance of flavors and in this case of the volatile composition. So I would like to thank your attention, and of course the financial support from the EAA grants, and also to my colleagues from NORS for microalgae, from Pagaretti Microalgae Solutions, and from Instituto Superior Técnico. Thank you so much.
Thank you very much. Muito obrigado, Cristiana, for this interesting and yummy presentation. And well, thanks also to Ismael and Julie for their presentations that made possible this webinar. I think they've all been quite interesting. And Stephanie and I are sure that you all have learned quite a bit about the new challenges involved when using algae, macroalgae or microalgae biomass in the development of different products. And now is the time for some questions for the audience. We have around 10 or 15 minutes for some questions about the presentations. So let's see if there is any questions that, so I think right now there is no question done by the audience, so don't be shy. Okay, if not, I don't know if Stefania, if you have any question, or we can do.
I have some. I have, for example, Cristiana told that the algae that they work are of food grade, but for example, Ismael and Julie, have you studied if your biopolymer that you extracted are of food grade?
Well, about me, I read yesterday some study about that, about its use as compost, but it doesn't say that it doesn't use food grade, but it has anti-food compounds that it can be used, for example, as fertilizer, so it won't be toxic for the for the worms and the bugs who makes the compost. But I think there is not a study yet in humans about its viability as food. So I'm still learning about that.
So a possible use of your algae is fertilizer.
I think that's for now, with the studies about the seaweed, I think it's the most fast use it can be done. But I think we will have to wait for more studies to come.
Okay.
And for example, I can answer for the carrageenan, for example. Yeah, it's already quite used in the food industry, for example, in milk or ice cream, but it's more like just a textural improvement, and not also an improvement of the taste of or adding bioactive compounds.
Okay.
Yeah.
And for Cristiana, I have another one. For Cristiana, are those changes in thermomechanical behavior really noticed by the consumers?
Not, it depends. For eye levels, they are noticed, yes. For the low inclusions, no, they are not detected by in terms of sensory panels, you say, yes, they are not detected. But for eye levels, we have differences in terms of texture profile, yes. The textural, the attribute, yes, we have.
I think there's one question
from Julie.
Julie, okay, I can read it. Does the incorporation of microalgae in food products increase their preservation? I guess
Yes, this is a very important question. Of course, there are some studies about this. In some cases, we have in the market. It depends from our previous experience. For instance, with this cheese company. In the beginning, we had some challenges when incorporating algae, because it was very difficult to obtain a final product in good microbiology conditions, because sometimes it depends, it is related with the stage when microalgae are added, because of course that microalgae, the final and the dried powder of microalgae, are sometimes contaminated. So we need to ensure that we apply a thermal processing during the food process. And it was we had these problems, but there are several, or not several, but a few publications demonstrating the impact in the bacteria, and they really help the storage of the products in terms of microbiology. Because of their antioxidant properties, they can decrease the level of some pathogenic bacteria, and this is already described in our project. We intend in the next steps will be to study these impacts during the fermentation of cheese, and at the present moment, we are working with sourdough bread. And as you know, sourdough is a consortium of acid lactic bacteria and some acetic bacteria. And we are adding the algae, not with the flour, but we are adding it to the sourdough. And in fact, it influences the microalgae, the microorganism, the bacteria. So it depends, because we need, of course, to be attention to this, which is the step. When are we adding the microalgae, if there are or not thermal processing or fermentation. Each product is different from the other, so it is important to select this study case with different. When we selected bread and cheese, it is because they have different thermal processes and compositions, of course, and the results will be different, of course. Thank you.
Okay, thank you very much.
Okay, I think there are more questions for Christiana. So
yes.
So I can read it. What happens if the percentage of algae is increased in cheese, for example, around 10%? Does it plateau after a certain point and causes destabilization of the structure?
In this halloumi and camembert-like cheese, we did not tested the Chlorella vulgaris microalgae at 10% level, because it will, in the camembert cheese, if we add 10% to the milk, it will means a lot in the final product, because during the production of the cheese, we have the release of the whey, so there is a concentration of the algae, and it will be impossible to eat. So the first challenge will be the flavor and taste. Anybody will eat, I think, a cheese if we incorporate algae at 10%. But of course, it will for sure influence the thermomechanical behavior. I've shown that it influence the mechanical behavior even at 1%. So of course, with 10%, we have different mechanical behavior, different mechanical spectra, and also hardness of these cheeses.
Thank you, Cristina.
So, I don't know, maybe if there is no more question, it's time to close the webinar.
I think it's...
So thanks again to all the presenters for making such a very nice presentations. To all of you for attending for this webinar. Carlos and me would like to take the chance to announce a new Polymers special issue that we are planning to run, named Biorefinery from Wastes to Biopolymers. And we are eager to receive your submission. And thank you a lot, thanks a lot, and see you soon.
All right, so let me just conclude with just a few words. So I want to take this opportunity to thank all the speakers and also the participants as well for attending this webinar. We hope that you gained some inspiration from today's talk and also look forward to meeting you at the next webinar. Thank you all again and have a nice day. Thank you.
Thank you very much.
Thank you.
Thank you.
Have a nice day.